Kinetics, lessons 11, 12, 13. Catalysts. A catalyst is an introduced substance which provides an alternate mechanism with a lower activation energy. Let's consider the following potential energy diagram. We'll use this potential energy diagram first to represent an uncatalyzed pathway. We can indicate the delta H for this reaction going between the reactants to products, and there's my delta H. Delta H is negative, therefore this is an exothermic chemical reaction, and we can also indicate the activation energy from the reactants to the top of the activated complex. If we add a catalyst to speed up this reaction, a catalyst is going to provide an alternate reaction mechanism, and it'll take a one-step mechanism and make it a multi-step mechanism. So in this case, I'm going to show a two-step mechanism. This would represent the catalyzed pathway. The delta H is exactly the same for the catalyzed pathway as the uncatalyzed, as the reactant and product levels are exactly the same, but what is different is the activation energy with a catalyst is much less. So there's our activation energy with a catalyst compared to the activation energy without the catalyst. A few notes about the catalyst curve that we've just drawn. The energy required, the activation energy, is less with the catalyst. So at the same temperature, more molecules can make it over the energy barrier, so the reaction rate speeds up. Catalyzed reactions usually involve more steps, but its highest activation energy is never as high as the uncatalyzed reaction. A catalyst never changes the potential energy of reactants or products. Only the route between them changes. Therefore, the delta H value for the uncatalyzed pathway and the catalyzed pathway is exactly the same. The uncatalyzed reaction still continues at its own slow rate when a catalyst is added, although it's usually insignificant. So the uncatalyzed pathway is still there. It does not shut down when a catalyst is added. If a catalyst speeds up the forward reaction, it also speeds up the reverse reaction. And a catalyst is used up as a reactant and then produced later in the reaction mechanism. So when we look at a mechanism, it appears on the left and also lower on the right. Let's look at a few examples here. For the following reaction mechanism, identify the overall balanced equation, the reaction intermediates, and the catalysts. I can identify S2O2HCl as an intermediate going from right to left. I can also identify S2O as an intermediate going from right to left. And I will identify HCl as a catalyst going from left to right. What we have left over is we have 2SO, H2, H2, H2O, S2, and H2O. So let's write our overall reaction, which will be 2SO plus 2H2 to produce S2 and 2H2O. So there's our overall. The reaction intermediates are S2 O2HCl, and S2O, and the catalyst is identified as HCl. For this reaction mechanism, we are to identify the missing step, which is step 2, and then what would be the reaction intermediates and the catalyst. Let's first identify the missing step. So I'm going to write my overall reaction. 2O3 plus energy going to 3O2. I'm going to take step number 1 and I'm going to reverse the step. And I'm also going to take step number 3 and call it 3 star and reverse the step. Now let's cross off what we can on either side. Energy can cross off. Oxygen and oxygen. O3 with one O3 there. O2 and O2 would cross off 2 oxygens there. And our missing step, step number 2, would be NO plus O3 to produce NO2 and O2. So there is my missing step, step number 2. Now let's take this back to our mechanism. So we have NO plus O3, NO2, and O2. Now let's then identify our intermediates and our catalysts here. Our one intermediate here is going to be oxygen. So oxygen. And another intermediate here is going to be NO2. And our catalyst here, going across from left to right, would be NO. So summarize this here. Our reaction intermediates are O and NO2, and our catalyst is NO. The assignment for this lesson is Hebden, pages 34 to 36, numbers 56 to 63.